Now let's look at what the simple type system that we've just presented actually guarantees. The type system guarantees that terms in the language are well behaved with respect to the underlying semantics. Our language has a semantics with reductions that are of the form an expression E evaluates to another expression E prime. This is a small step reduction semantics. I'm not going to present the small step reduction semantics here. Let's just say that we know the semantics of the lambda calculus, but once we have the semantics, we have two properties of the type system. The first is that if an expression E is well typed and E reduces in one step to E prime, then E prime is also well typed and has the same type. This theorem is usually called a subject reduction result, and this is a result about type preservation. And of course you want your type system to guarantee that if you are well typed, then you stay well typed as you perform a computation step. The other theorem that we want is a result about type safety. And the type safety result says that well-typed terms do not go wrong. More precisely, what does that mean? For the simply typed language, well, it means that if an expression E is well typed with type T, then E terminates. What does it mean that an expression terminates? It means that there is an E prime such that if E reduces in some number of steps to E prime, then E prime cannot reduce any further. So that's true for the simple type system. Both of these theorems hold for the simple type system. Of course, this result about termination also says that the simple type system is not so powerful, because sometimes we want to write programs that may not terminate or should not terminate. So there are definitely interesting and useful programs that you cannot express in this language and have them well typed. So the type system is not so powerful. One way of seeing that something is amiss and there's something that cannot be captured by this type system is to notice that the type system has slack. To see this, notice that first it's the case that if we consider the class of well-typed expressions, well, they all terminate. But now let's look at the class of safe expressions. Then there are expressions that are safe but not well typed. An example of that is let f be lambda x dot x in f naught comma f of true. This expression terminates, obviously. It should evaluate to the term naught point true. So it terminates, but it's not well typed, and the reason why it's not well typed is that we cannot find a type. for f. Because if we try to find a type for f, we can't. Let's have a look at what happens if you want to try to type f. The problem is simply that when we consider f of naught and f of true and the pair of those, then if we have a function lambda x dot x at our disposal, then is the type of f integer to integer, or is the type Boolean to Boolean? In the simply typed language, we have to choose. But it would be nice if we wouldn't have to choose. Because the identity function could take any argument and return a value of the same type. It would be nicer if we could say that f had type A arrow A for every type A. And that's parametric polymorphism. And we're going to introduce that now.